So we will now solve this problem. Get on to this. It says a solid circular shaft of 100 mm diameter transmitting 120 kilowatt at 150 rpm. Guys, basically we transmit power using shafts. So shafts could be like this, circular shafts like this. So basically it would look like this, and this will have some diameter. And the power which is being transmitted, is 120 kilowatt, 120 kilowatts of power, and that is being transmitted at an RPM of 150 RPM, 150 RPM. And we need to know the torque here, because we need to know the torque, because in the formula of the torsion, we know the formula for the torsion: tera, towel, ganda, theta, jaldi, rin, lagao. That is the formula that we actually said last time. So we are supposed to use this part of the equation to find out the maximum shear stress. So we are supposed to find T. Now we're supposed to find T. We know what is J and what is R, and we're supposed to find T here. So we know that by the formula P is equal to 2 pi nt by 60. 2 pi nt by 60. When this n is given in RPM, you should divide this by 60. Okay, now n is given in RPM, so I'm dividing this by 60 because this is actually 60 seconds here to convert into per second. Okay, so here now I'm substituting power here. What is power? Power is 120 kilowatts. I know power is 120 kilowatts. Is it visible? Okay, 120 kilowatts. You know, 120 kilo is 10 to the power of 3. 10 to the power of 3. You know, each watt, 1 watt is nothing but 1 Newton meter per second. So I substitute this watt unit as Newton meter per second. So you know 1 Newton meter is joule, joule per second is watt. So therefore this 120 kilowatt is written as 120 into 10 to the power of 3 Newton meter per second. So I substitute this here, I substitute this here. So 120, so I can substitute this this as 120, okay, anywhere here, 120 into 10 to the power of 3 Newton meter per second. So let us substitute these values here. So here T is equal to, so this 120 into 10 to the power of 3 Newton meter per second, and the 60 seconds goes upwards. Seconds gets cancelled here. Seconds will get cancelled here. Very sure about this? Second and second will get cancelled here. And then this 2 pi comes below. 2 into pi comes below. And n comes below. So what is n? 150 rpm. N comes below and only T is remaining. So 2 pi n is coming below and the 60 goes above. So this is how it is. Now what is left here? Basically unit. What is left is Newton meter. So what is the answer, man? Huh? 763.99. So which you can call it as 764 Newton meter. 764 Newton meter. So this is the amount of torque which is being transmitted. So that means, suppose if this RPM was larger, then this torque would have got smaller. So if you're trying to transmit power, usually we transmit power at higher speeds so that the torque becomes less. If you're transmitting torque at lower speeds, if you're transmitting power at lower speeds, then the torque is larger, then the shaft has to be larger. Okay? So here with this lower speed of 150 rpm, so it is now taking a huge amount of torque of 764 Newton meter, which has to be substituted here. Okay? So let us substitute this value here and see. So let me, there is this part here. So let us substitute this.
We were getting 7639.
7639. It's a very large number. 7639. Okay. Guys, anybody has checked else? Who else? Okay, 7639. Okay, 7639 Newton meters of torque. Okay, so thank you for the corrections. And now here I am substituting this, and before I substitute this, I know what is actually JP, polar modulus of. So what is actually JP formula? JP for circular shafts. JP for circular shafts. A shaft which is circular. What is JP for this? Polar modulus of. So it is a circular section. What is the formula? Pi d to the power of 4 divided by 32. So it is half of. It is actually half of section modulus. Okay, it is half of section modulus. So pi d to the power of 4 divided by 32. So, and then you know R is nothing but d by 2. R is nothing but d by 2. D by 2. Okay. Here anyway they have given the diameter here. They have given the diameter. So you can substitute this values here. So JP is equal to pi into d, which is actually 100 mm. 100 mm to the power of 4 divided by 32. Okay, here it is. Suppose if you don't want to substitute here, you can actually cancel out this. This R and R goes, this D and D goes, it will become pi d to the power of 3 divided by 16. So you'll understand if suppose if this is brought below here. Okay, then it becomes pi d cube divided by 16. So I think it will be easy for you. So you can, okay, it's left to you how you do it. And then 100 mm. Some people do that way, some people do this way. It's left to you how you do it. 100 mm. So now once you have done this, you substitute these values here. You substitute these values here. I am now substituting these values here of T. So T, which was found as 7639 Newton meter, divided by, what is the value of this, guys? Any answer that you got for this? 9817 477, huh? 77. Okay. That's it, huh? Point? 0.04. Okay, leave it. No issues. Millimeter to the power of 4. Okay. What about this? 100 divided by 2? That is 50 mm. 50 mm. And here we are now supposed to find shear stress tau. So you can actually get this tau here. What is the answer for tau? So usually, can you guess an answer for tau? You know what is the values of shear, normal stress that you have now, usually for metals. What is the value? 250 to 500. 250 to 500. Okay, it can go up to 800. And we know shear stress has to be half of the normal stress. So usually it should be around like 200 to 300 or something. Now what is the answer that you got? Shear stress? So you can check out this values here. Now the shear stress units is Newton per mm square. Guys, here, if you see here, millimeter and this becomes, these are actually like this. I think units are balancing. Meter divided by millimeter cube. Sorry, millimeter to the power of 4. It becomes millimeter to the power of cube here. And here also, millimeter square. If it comes here, it becomes millimeter cube. So units are balancing. So you should substitute. People may think, why you got this units as Newton per mm square? Why not other things? Now if this equation has to be balanced, it has to be Newton per mm square here. Okay? Here it is meter divided by millimeter to the power of 4. Here it is, okay, here it's in the denominator. Here it's in the denominator, so it comes here. It is millimeter to the power of cube. Okay? So, you please understand, so you got this units. So, anybody got the answer? Shear stress? 38.90, which is a very small value. 38.90, which is definitely a safe value. because usually metals can go up to 250, means half of it is 125. So it is well within the limits. Okay, so you got this shear stress which is 38.90 Newton per mm square. So this is how you solve a numerical. So